Welcome back. So, as of now, we have completed Unit 1. Under Unit 1, we have studied the different waveform coding techniques like pulse code modulation, differential pulse code modulation, delta modulation, and adaptive kind of modulations. And now in this Unit 2, we are going to study channel coding techniques and line codes. After completing this unit, you may be able to design an encoder and a decoder for a better error control in your system. In this lecture, we are going to discuss about the basics of error control codes and its classification. Also, we are going to discuss the terminologies of block codes. I would like to recall the block diagram of a digital communication system. In this block diagram, the formatter consists of the formatter part we have completed under Unit 1. This formatter consists of sampler, quantization process, and encoding process. So the input of this formatter is the analog signal, and the output of the formatter is binary data. And the kind of technique used in the formatter is called as waveform encoding techniques. The source encoder is used for compression, which is used to reduce the redundant information. So that the bandwidth will be utilized as much as possible to transmit large number of data and large amount of information. And then encryption is meant for security purpose and authentication purpose. And an important block called as channel encoder. And in this unit, we are going to briefly study about the channel encoder. This is used to detect the errors and correct it. This channel encoder will add some redundant information. Add redundant information along with the information data so that at the receiver side it can be able to detect the error which had happened due to the presence of additive white Gaussian noise channel as well as different effects of the channel, and to correct it. There are two different techniques will be used at the receiver side. The different techniques are forward error correction method called as FEC and The next method is called as automated repeat request, which is called as ARQ. In FEC method, the receiver will have the correction capability of the erroneous bit, whereas in the case of automatic repeat request, the receiver will only detect the errors and it will not correct the error. Instead, it will ask the transmitter to transmit the information once again so that the correct data will be received by the receiver. So the channel encoder will be present at the transmitter block and the channel decoder will be present at the receiver block. So these two will be synchronously operated at both the transmitter end as well as at the receiver end to have a better control over the errors which are all occurring due to the presence of various effects in the channel. While we transmit the binary information over the channel with the help of pulses, let me say one example 1 1 0 1 1 0 1. This is the binary data. If the noise is present in such a way that if the noise is present like this, then the output will be, the received signal will be so we will receive this signal at the receiver end. So if the threshold is fixed like this, the threshold is fixed like this, the receiver will decide this will be 1, this as 1, this as 1, this as 1, this as 0, and this as 1. As the signal is greater than the threshold value, if this is the threshold amplitude, the receiver will consider all these informations as 1 and this information as 0 so that it will have one error bit in this position. If this error is identified by the receiver, then receiver can do any one of these two techniques. If the receiver is having a channel decoder which is having a error correcting capability, then it will correct the error and it will send the data without any error to the next signal processing block. But whereas if the channel decoder is not having an error correcting probability, then it will request the transmitter to forward the data packet once again so that the receiver can able to receive the data without any error. And this kind of repeated request will happen until it receives the information without the error. So error control codes are otherwise called as channel codes. Error control codes is otherwise called as channel codes, which is used to add some redundant information along with the payload information in order to determine where the error has happened at the receiver side, and also it is used to correct the erroneous bits present in the received data packets. And this error control code can be categorized depending on several parameters such as mapping, number base of the message, encoding operation, algebraic structure of the code word, and error correction capability. If the code is having a proper structure and the codes are arranged in a way which is representing its useful meaning, for example, if it is represented, that is, if message bits and the redundant bits, and if it is defined by some standard method, then it is called as systematic codes, and if it doesn't represented by some systematic manner and the redundant information are placed in between the various positions of the message bits, then it is called as non-systematic codes. And the error control code is again classified with the help of numeric base of the message. If the binary codes, for example 11010001, likewise the message bits are present with the help of binary data, then that type of channel coding is called as binary channel codes. If it uses some another code word like code word bits, like code word data like hexadecimal or octal, then it is called as non-binary codes. And based on how we are going to design an encoder and how we are going to do the encoding and decoding operation, the channel codes are classified into two different types that are all called as block codes and convolutional codes. If the codes are being generated without any memory requirement or without depending on any previous values, then it is called as block code. It only involves the combinational circuits for generating the code words. Then this kind of code words is called as block code. And another type of code word is there, which is called as convolutional code, which involves the previous binary information, previous message bits to generate the code word, and also involves memory requirement and uses the sequential logic circuit. In its encoder and decoder design, then this type of codes are called as convolutional codes. Then based on the algebraic structure of the code word, the channel codes can be classified into two types, linear codes and non-linear codes. If you add two different codes, then it will produce the third code in the code word table. Then it is called as linear code words and it satisfies the superposition principle. Or additivity property. If it satisfies these two properties, then it is called as linear codes, or otherwise the code is called as non-linear code. And depending upon the capability, the codes are classified into two types further. Those are called as error detection codes and error correction codes. If the codes are only having the capability to detect the error and it doesn't having the capability to correct it, it is called as error detection codes. Whereas if the codes are having the capability to correct the errors, it is called as error correction codes. In error detection codes, the system will use automatic repeat request procedure to receive the correct information from the transmitter. Whereas if the receiver employs the error correction codes, then it will use the forward error correction methodology to correct the erroneous bits at the receiver end. Let us discuss with the systematic code. Here we are going to consider a message bit which consists of k number of bits. Let us assume a message word which consists of k number of bits. Let assume m0 is the first bit, m1 is the next bit, and it consists mk minus 1. That is, we are having k number of bits in the message word. If it is assumed like this, then this k number of message bits will be added with some number of redundant bits, or otherwise called as parity bits. Let we assume the parity bits as b not b1 and up to bn minus k minus 1, so that we will have n minus k number of parity bits. If we add this n minus k number of redundant bits along with the message bits, we will have totally n minus k plus k number of bits in the code word, which will be equal to n bits. So the number of bits in the code word is n. And the number of bits in message word is equal to k. If the message word and the code words are arranged in such a way that if the parity bits are padded in the most significant position, and the message bits are located on the least significant position, or otherwise the message bits will be on the most significant position and the parity bits are located on the least significant positions, then this kind of code is called as systematic code, because it is having a systematic arrangement where the parity bits or the message bits are grouped together and located either on the most significant position or on the least significant position of the entire code word. So there will not be any confusions in the positions of the parity bits as well as the message bits. They are grouped together as alone, and both the parity bits or message bits are combined together in a well structured positions. That's why this code is called a systematic code. On the other hand, if the message bits and parity bits are located in such a way that let m0 will be the most significant bit in the code word, and then b0 will be present, then m1 will be present, then b1, b2 will be present, and likewise it will go up to the last word. Either it may end with any parity bit, either b0, parity, or the last bit of the message. and the code word will be formed in this way. And this will not be same for all the types of non-systematic code, and another type m0 m1 will be placed and b0 m2 will be placed, m2 b1 will be placed. Likewise, the placement of locations in the bits will differ from one case to another case, and those kinds of codes are called as non-systematic codes. And if we employ the binary data for encoding and decoding operation, then it is called as binary code. If the codes does not involve the binary data but involves some another representations like octal, decimal or hexadecimal, and those kinds of codes are called as non-binary codes. And depending on the circuit or the operation which is involved in the encoding and the decoding process, the codes can be categorized into two different codes, block codes and convolutional codes. Generally, the block codes are called as n, k codes, whereas n is the number of bits in the code word, whereas k is the number of bits in the message word. So it uses a specific mathematical logic or a mathematical Boolean logic to generate n number of bits at the coder. Suppose if this is a encoder of the block codes, it will generate n bits at the output by considering the k bits at the input. And the encoder will be implemented with the help of combinational digital logic, which uses only the different gates, logic gates, such as AND, NOT, OR, NAND, NOR, XOR, and XNOR. Then this kind of codes are called as block codes. And this will not involve the memory requirement, as it only uses the simple Boolean logic gates. And the implementation will be very easy. And another kind of code which involves the memory requirement for encoding the message bits to produce the code word and uses the sequential logic circuit. The convolutional codes involves sequential logic circuit. In the encoder, which uses the memory requirement. That is, it is having combinational circuit. Sequential circuit can be using the combination circuit and memory requirement. Memory will be there and it will be given to the input. So the output of this encoder depends upon the present message data as well as the previous code word data. Then this type of codes are called as convolutional codes. And it depends upon the current state and the previous states of the encoder. Then there are two classifications depending upon the property, linearity property. If the system satisfies, if the codes satisfy the superposition principle, then it is called as linear codes. That means if you are having in an n comma k code, n comma k channel code, you may have 2 power k number of distinct code words. This is the first code word, second code word, and up to 2 power k. So if you add any of the two codes in the code word table, and this is called as code word table. Because any encoder is having k bits at the at its input and n bits at its output. So we are having 2 power k number of possible inputs that can happen at the input of the encoder. Similarly, the encoder will produce the same number of, that is 2 power k number of possible different outputs at the output of the encoder. Hence, we will have 2 power k number of code words, and the group of different possible set of all code words is collectively together is called as code word table. If you add any two code words in the code word table, if it produce another code word in the code word table, then it is called as linear codes. And in this way, if we add two code word, two same code word, then it will produce a zero code word. Because here we are using modulo 2 addition logic. For an example, if a code word is represented like this, and another code word is represented like this, then if you add 10110, 11010, and the modulo addition of these two will be like 000, 110, 101, 1011, and 110. The modulo 2 logic is nothing but, this is called as modulo 2 logic. Modulo 2 logic is nothing but the NAND implementation. Sorry. Modulo 2 logic is nothing but XOR implementation. So if both the data are same, then it will produce 0. Both the binary data are different, it will produce 1. Okay, so if these two are the code words in the code word table, and this is also one of the code word in the code word table, then it is called as linear code. And if you add the same code word with the same, then it will produce all 0 element. And that kind of code word is also present. All 0 code word is also one of the code word in the code word table in case of linear code word. Whereas if it does not satisfy the superposition principle or the linearity property, then that type of code word is called as non-linear code word. And depending upon the capability, we can classify the code words into two different types: error detecting codes or error correcting codes. Block code, any block code can be represented by n comma k block code, where n is the number of code word bits, and whereas k is the number of bits in the message word. And as we have already discussed, the encoder of the block code consists of k number of input, k number of bits at the input, and the output, let we assume this is m of 0, m of 1, and up to m of k minus 1, because this message will be represented as m naught, m1 up to mk minus 1. And m naught is the most significant bit in the message word, whereas mk minus 1 is the least significant bit of the message word. And the encoder will produce the code word which consists of n number of bits. And this block code adds the message bits. This code word will be structured in a way C naught will be in the MSB position and Cn minus 1 will be at the LSB position. And it creates or generates n bit block which is called as code word. And this block will be represented, this code word block is generated with the help of k number of message bits and n minus k number of parity bits. The parity bits are added redundantly along with the message bits to generate the n number of code words. N number of bits in the code word. So these block codes can be represented in a systematic form or in the case of non-systematic form. If it is in the systematic form, the parity bits are either added at the beginning or at the end of the code word. A simplest type of block code is called as the parity check codes. It consists of two different types, even parity and odd parity. If the parity of a binary code is known as even, if it contains even number of ones, then it is called as even parity. Similarly, if the code word is consisting of odd number of ones, then that kind of parity is called as odd parity. Suppose if this is the message word, if you want to add even parity, then you have to add 0. If you want to add odd parity, you have to add, even parity, you have to add 1. If you want to add odd parity, you have to add 0. This parity bits can be either padded at the end or at the beginning. This is one case, and another case is the parity can be added on the beginning of the code word in this way. If this is added like this is called a systematic format. If this code word is present, if the parity bits are present in any part of the message block, then it is called as non-systematic code. And if a single error occurs in the message at the receiver, then the parity check code can detect that error and it is failed to correct the error since we are unable to identify in which bit the error has happened. That's why the parity check code is basically called as error detecting code and is having the capability of detecting the error alone. and it cannot able to identify in which position the error has happened. That's why it fails to correct the error. There are few terminologies in block quotes. The first terminology is called as word. The word is nothing but a sequence of symbol. We are calling the message as message word and the code as code word. The message consists of k number of bits, and whereas the code word consists of n number of bits. So a group of bits are collectively together and called as word. The next metric is called as Hamming weight. The Hamming weight of a code word is equal to the number of non-zero components present in it, or otherwise we can say the number of ones present in the code word. Let we assume a code word 1010. Let it will be the ith code word in the code word table. Then the weight of this ith code word 4-bit binary code word will be 2 because it consists of two number of ones. And that's why the Hamming weight of this code word is 2. The Hamming weight of the ith code word will be represented by either Wi or W of the code word Ci. Weight of the code word Ci. And the next performance parameter is called as Hamming distance, which is nothing but the distance between any two binary blocks, or otherwise the distinct number of places between the any two code words in the code word table. So let us consider one example. Here we are going to determine the Hamming distance between two number of 4-bit binary code words. For that we are going to take two code words from the code word table, that is ith code word and jth code word. Ith code word is 1010 and jth code word is 1101. Now we have to identify which positions or how many number of positions are having different values, different binary data. So the least significant bit is different. The next significant bit is also different, and the third significant is also different, and MSB is also different. Sorry, MSB is same. So there are three number of different positions. That's why the Hamming distance is represented as 3. And the Hamming distance between the ith and jth code word is represented by Dij, or otherwise distance between the code word I and the code word J. That is D of Ci, Cj. And this Hamming distance can also be determined with the help of performing the modulo to addition of those two code words and determining the Hamming weight of the resultant. For example, the code words here represented are 1010 and 1101. Now, if you do the modulo to addition, you will get 011, 101, 011, 10110. So now you have to find out the weight of the resultant code word. And the weight of the resultant code word will be determined by counting the number of ones in the code word, which is having 3 number of ones. So the Hamming distance is also determined with the help of determining the Hamming weight of the two code words. Then is the minimum distance. The minimum distance of a code word is nothing but the smallest Hamming distance between all possible pairs of the code words present in the code word table. So this dmin, minimum distance dmin, can be written as minimum of all the possible values of distances of two code words where I not equal to j. Because if I is equal to j, then the distance will be determined for ci comma ci. So in the previous case, we have taken 1011 as the ith code word. If you find out 1011 and 1011, so no positions will have the different values. All are having the same values, so that the distance will become 0. So we should not take the 0 value as the minimum distance. So the minimum distance should be always greater than 0. The minimum distance should be always greater than 0. And the minimum distance of a code word will always be equal to the minimum weight. The minimum weight of a code word the minimum weight of a particular code n comma k block code is determined by identifying the smallest weight of any non-zero code word. So if you are having 2 power k number of 2 power k number of code words in the code word table, and if it is consisting of all 0 any element, then the Hamming weight will be 0. So this should be discarded. And we have to find out the weights of each of the code words. Let it will be weight 1 and it will be weight 2 power k. 2 power k minus 1. And we have to find out the minimum value of wk w1 w2 up to wk minus 1, sorry, w2 power k minus 1. Then we can able to identify the minimum weight. This is the way how we have to find out the minimum weight. And the minimum distance is equal to the minimum weight. Generally, if you want to find out the minimum distance, always we go for minimum weight, because the comparison will be very minimum. Because here we have to only compare the 2 power k number of possible data. But whereas in the case of minimum distance, we have to find out all the 2 possibilities from the 2 power k data. So the minimum distance can be easily found with the help of identifying the minimum weight. And another important, very important parameter is called as code rate, which is involved in determining the data rate of the system, as well as there will be a considerable significant in determining the bandwidth requirement. And the code rate of any n comma k code is determined by a ratio between the number of message bits to the number of code word bits. The minimum distance of a block code is used to determine the error detection and error correction capability of the code. If the dmin is odd, then it can able to correct dmin minus 1 divided by 2. If dmin is even, then dmin by 2 errors can be detected and dmin minus 2 divided by 2 bits can be corrected. Let us say if dmin and error detection capability and error correction capability. If dmin is 1, then 0 bits can be, because 1 is an odd number, so d min minus 1 divided by 2 errors can be corrected, so 0 errors can be corrected. If d min is equal to 2, then 1 error can be corrected and 0 error can be detected. Sorry, 1 error can be detected and 0 error can be corrected, errors corrected. And if d min is equal to 3, then it is an odd number, so 1 bit of error can be corrected. If it is 4, then 2 bits can be detected, 2 erroneous bits can be detected, and 1 bit can be corrected. So this is the way to determine the possibilities of error detection and error correction capability of a particular channel code. So these are all the various parameters which is used to determine a block code. In the next class, we will briefly discuss about the different types of block codes.